All right, finally, a moment I've been building up to for a long time in this class. So what I would like to do right now is take Euler's equation and show you how to obtain Bernoulli's equation or Bernoulli's theorem from it in just a couple of lines, really. So let me tell you what Bernoulli's theorem is, and then I'll use Euler's equation to obtain it. So Bernoulli's theorem states that along a streamline, a quantity is conserved or is constant, and that quantity is given by half rho v squared plus pressure plus rho gz. That quantity is a constant along a streamline for steady, incompressible flow where viscosity is taken to be zero, but in reality, in practice, it's unimportant, not necessarily exactly zero. Four important assumptions here. So that quantity is conserved along a streamline for steady flow, meaning that the velocity, if given in the Eulerian description, the partial derivative with respect to time of the velocity vector is zero. This is true for incompressible flow where the density is a constant everywhere, or at least along a streamline, and effectively inviscid flow. So viscosity is taken to be zero. In reality, what we mean by that is that entropy doesn't change along the streamline. So it turns out that viscosity is the mechanism by which entropy gets raised in a fluid. But so anyway, so for an inviscid flow or an isentropic flow, that's when this applies. All right, so here's the proof. What I'm going to do is take Euler's equation. So that's density times acceleration, where that acceleration is written using the material derivative, equals minus delta P, or not delta, the gradient in pressure, plus rho times G, where G is a body force per unit mass. Okay, so what I'm going to do is I'm going to take Euler's equation and dot it with velocity. So that leading term becomes v dot acceleration equals minus v dot gradient of pressure plus rho v dot G. And then what I'm going to need to do is do a little bit of work on each of these terms to make them look like a way where I can actually integrate them. The first term is the most important term here, and it won't take me that long to actually manipulate it. So let me just rewrite that term. So that's rho times v dot acceleration, which is dv dt, and I need to figure out a way to simplify that. So I'm going to do it a little bit reverse. I'm going to show you what the simplification is, and then I'm going to prove that it's equivalent. So let's look at what the material derivative of half v squared is. I can use the product rule to show that that's half dv dt dot v plus half v dot dv dt. That's just like the product rule. And because the half appears in both things, the half from the two terms that are identical add, and you just get v dot delta v. Therefore, that thing that is exactly equal to the leading term there. So what I can do is write rho v dot dv dt is ddt, the material derivative of half rho v squared. If I look at what's inside that derivative, so the half rho v squared is just some scalar, right? So what I should do is actually write out the material derivative and apply it to each of the terms in the scalar. But the thing is that velocity doesn't depend on time because we have, or the partial derivative of time, because we have assumed that it's a steady flow. So in that case, only the back half of the material derivative, the convective derivative, survives. And I get v dot gradient of half rho v squared. Or if I do that along a streamline, it's actually a little bit easier to write because the gradient always points along the streamline. So that would be v dds, where that's like the directional derivative along the streamline. That's the gradient in streamline coordinates. And then the thing that it acts on is half rho v squared. So that's term one, the first term that showed up in Euler's equation when dotted with v. Then we need to work on the other terms. So the second term, which was v dot pressure gradient, That's actually already simplified enough, but I can write it in streamline coordinates, which is minus v dp ds. So basically I'm just going to change it. So in streamwise coordinates, the velocity is pointing along the s direction, or the s hat direction. So v dot gradient is just v d ds. So the term you get is minus v dp ds along the streamline. So that's term 2. And then the final term involved gravity, or the body force. So that was rho v dot g. But usually I have a particular form of g in mind if it's gravity. So I'm going to restrict this to gravity. So if the g vector is minus g times k hat, as in like gravity, then you can actually write the body, or like v dot g, in terms of what I'll call like a potential, which is minus g times z. So like obviously if I take the gradient of that, I'll get the right thing to come back. So I can also write that in streamwise coordinates. So like I can take minus v dds of rho g z, and that's an equivalent way to write it, where now I'm taking the gradient along the streamline. So that gives me the third term. If I put those three terms together, there were only three terms, so now I've got them all. And you'll see that when I put that together, I've now got them all kind of in a similar looking form. So v ds of half rho v squared is equal to minus v, the magnitude of v, dp ds, minus v dds of rho gz. You can see that there's like a v dds in front of each one of these terms, and so I can basically gather things inside of the derivative of dds and set that all equal to 0. So because everything's inside of the derivative, I can basically, I can divide by v and then integrate with respect to s. So integrate along the streamline, and I'll find that half rho v squared plus p plus rho gz is equal to a constant along the streamline. Now it's important to point out that I did that integration along the streamline, like I integrated a scalar with respect to s. That actually doesn't tell me anything about how it changes in the normal direction. So like if I'm not going along the streamline, that quantity can change in some cases. And like in the general case, it does change. So this really only applies along a streamline. So to apply Bernoulli's theorem, you have to identify a streamline along which a fluid particle moves in order for it to be useful. So in summary, there are 4 assumptions built into Bernoulli's theorem that you need to keep in mind. They're not usually that hard to satisfy, but you have to keep them in mind. So the first assumption is that it's incompressible flow, so the density is a constant. That's not usually a very hard assumption to hit unless you have like a high Mach number flow or very extreme changes in pressure. Steady flow, meaning that the velocity locally does not change with time. That's also usually not hard to satisfy. The ability to identify a streamline might be difficult if you don't know what the flow pattern looks like, but it's usually not a problem, I would say. The last one is the hardest one to really justify, I think, but we'll talk a little bit more about it coming up, and that's inviscid. So what you really need is for the viscosity to be so small that it's totally unimportant. Or in other words, this was derived assuming that the viscosity was equal 0 and there's no shear stress. In practice, you don't actually need the shear stress or the viscosity to be 0. In fact, it's never 0 for any fluid. What you really need is the magnitude of the shear stresses to be much smaller than the pressure gradient. And we've actually already seen in class that that happens when the Reynolds number is really large. So what we don't really need the flow to be inviscid. What we really need in order for this to apply in practice is to have large Reynolds numbers. Large Reynolds number implies that the pressure gradients are much larger than the shear stress that will exist in a flow. So that's the main condition that we need, large Reynolds numbers. And we'll see that for a lot of situations of engineering interest, that will be satisfied.